Hi, hello dear students. Welcome to physics class of U2. So we have been discussing about the chapter nuclei. In the previous class, we have discussed about the Einstein mass energy equivalence relation, that is E is equal to mc square. That means what? The mass can be converted into energy or energy can be converted into mass. Then we have seen about the mass defect delta M. That is, mass defect means difference between the sum of masses of the nucleons forming the stable nucleus and the mass of the nucleus in the stable state. That difference between these two is called as what? The mass defect. And also we have discussed about the binding energy, and also we have discussed about the binding energy EB, that is equal to what? This mass defect into c square. That the amount of mass lost during the formation of the nucleus from its constituent nucleons, that is the liberated in the form of that is used as energy to bind the nucleons to form the stable nucleus, right? So the binding energy is equal to what? Delta M into c square. Now also we have given one relation here in the previous class, that is the 1 AMU amount of mass, which is equivalent to energy in terms of electron volt, is 931.5 mega electron volt. Electron volt, it is the unit of energy which is used in atomic and nuclear physics to express the energy. And electron volt, 1 electron volt, it is equal to what? The energy, kinetic energy gained by the electron when it is accelerated through a potential difference of 1 volt. Right? That is 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Now these all relations we have discussed in the previous class. Now the next point we have to discuss here related to this, and also we have solved one numerical, that is the calculation of mass defect and the binding energy of the helium nucleus. Now let us solve here one more example, calculation of the mass defect and the specific binding energy of the iron nucleus, that is Fe26. Before that, let us see here what is meant by specific binding energy. Specific binding energy. What is meant by specific binding energy? We have to define here, then we will calculate the mass defect and specific binding energy. So specific binding energy is also called as what? The binding energy per nucleon. Binding energy per nucleon. And it is denoted by the symbol EBN. It is equal to what? EBN, and it is equal to what? The total binding energy. Total binding energy divided by mass number. That is called as what? Atomic mass number. That is called as the binding energy per nucleon. That is EB divided by A. That is called as what? The binding energy per nucleon. It is equal to what? The specific binding energy. It is equal to the ratio of total binding energy of the nucleus to its atomic mass number. That is called as what? The specific binding energy. Right? It's a very simple formula here. Binding energy per nucleon, it is equal to binding energy per nucleon, it is equal to total binding energy divided by mass number. So let us take here the example of iron nucleus, and let us calculate here the specific binding energy. Before that, we have to calculate binding energy. To calculate the binding energy, the calculation of the mass defect is required. Right? So one more time I will repeat the definition of specific binding energy. It is equal to the ratio of binding energy of the nucleus, total binding energy of the nucleus, to the total number of nucleons present in it. total number of nucleons present in it, that is equal to the what? The atomic mass number, right? The ratio of total binding energy of the nucleus divided by the total number of nucleons present in the nucleus, that is equal to the mass number. Now, with all these, the definition of the specific binding energy, now let us calculate here the mass defect and the binding energy, specific binding energy of the iron nucleus. So, to calculate the mass defect, what is the formula? Delta M is equal to mass defect is equal to what? Right? That is equal to ZMB plus A minus ZMN. This is the mass of the sum of masses of the nucleons in the free state, and the minus the total the rest mass of the nucleus in the stable state, that is after forming the nucleus. This is the sum of the masses of the nucleons before forming the nucleus, right? This M is what? The mass of the nucleus after forming the stable nucleus, right? Now, with all these values, by taking an example of iron nucleus, the number of the atomic number is 26. That is 26 into mass of the proton is 1.00783. Next, plus A minus Z, that is the number of neutrons. It is equal to 30 into mass of neutron is 1.00867. Then minus, that is the mass of the iron nucleus, that is major mass of the iron nucleus, that is equal to what? 55.493, right? It is all these masses are given in terms of AMU, right? So after solving this bracket, you will get the answer is, and final answer I will write here, that is equal to 0.528461. 528,461. 528,461 EMU. So this is the mass defect we are observing in the formation of iron nucleus from its nucleons, constituent nucleons. So ಇಲ್ಲಿ ನೋಡ್ರಿ separate nucleons ಇರ್ತಾವ, ಅದರ ಮಾಸ್ ನಾವು ಇಲ್ಲಿ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ಫಸ್ಟ್ ಆ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ನಿಂದ ನ್ಯೂಕ್ಲಿಯಸ್ ಫಾರ್ಮ್ ಆಗ್ತದೆ, ಅವಾಗ ಏನು ಮಾಸ್ ಬರ್ತದೆ ಅದನ್ನ ಬರ್ಕೊಳ್ತೀವಿ. ಅವು ಎರಡು ಡಿಫರೆನ್ಸ್ ತಗೊಂಡಾಗ, ಇಫ್ ಯು ಹ್ಯಾವ್ ಟೇಕನ್ ದ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ ಟು ಬಿಫೋರ್ ಫಾರ್ಮಿಂಗ್ ದ ನ್ಯೂಕ್ಲಿಯಸ್, ಮಾಸ್ ಆಫ್ ದ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್, after forming the nuclear mass, if you observe some mass is lost, we are getting some positive term here, right? That is not equal to 0, that means some mass is lost. That mass is converted into energy, that is called as what? The binding energy. And this is the mass defect, right? This is the mass defect we have observed, that is missing of mass or loss in mass during the formation of stable nucleus. Now we know the relation here is equal to 1 AMU. If 1 AMU amount of mass is lost, then the amount of energy converted is equal to 931.5 mega electron volt. 1 AMU amount of mass loss ಆಯ್ತಂದ್ರೆ ಅದು ಎಷ್ಟು amount of energy ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದ್ರಿ? 931.5 mega electron volt ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದೆ. So then we know that we can calculate the energy here by using the binding energy. So binding energy is equal to, after binding energy we have to calculate the specific binding energy. So binding energy EB is equal to what? The mass defect into C square. You can use this relation, or we know that the relation between the AMU and energy, that is the relation between AMU and the energy. If 1 AMU amount of energy is lost, mass is lost, the amount of energy converted is this one. Now if this amount of mass is lost, just we have to multiply with 0.528461 to this one. So therefore EB is equal to 0.528461 into 931.5. So then binding energy is equal to, that you will get as the binding energy of the iron nucleus is 492.26, 492.26, 492.26 mega electron volt. That means what is meant by binding energy? The amount of energy required to bind the nucleons to form the nucleus, right? So next one, we have to discuss here why this binding energy is required, because we have to introduce the one more concept here, the nuclear force, right? So EB, binding energy, is equal to what? 492.26 mega electron volt. So this is what the binding energy. Then what we have to calculate here? The specific binding energy. Specific binding energy is equal to what? The binding energy divided by its atomic mass number, right? So binding energy is equal to what? Specific binding energy is also called as binding energy per nucleon, right? One nucleon ಎಷ್ಟು energy ಬೇಕಾಗ್ತದೆ ಅಂತ ಹಿಂಗಾಗ್ತದೆ. So B divided by A. So B is equal to what? 492.26. Atomic mass number of iron is 56. So 492.26 divided by 56, it is equal to 8.79. It is equal to what? 8.79 mega electron volt. So the binding energy per nucleon of the iron nucleus is equal to 8.79 mega electron volt. So this is the total binding energy of the nucleus. This is what the binding energy or the binding energy, specific binding energy per nucleon. Per nucleon कैसे energy ಬೇಕಾಗ್ತದೆ ಅದಕ್ಕೆ ಏನಂತ ಕರೀತೀವಿ ನಾವಿಲ್ಲಿ? It is called as what? The binding energy per nucleon or specific binding energy. So this is the very important numerical on the chapter nuclei. So in the previous examination they were asked in the 2020 in the supplementary examination they have asked 5 mark question. 2020 supplementary examination 5 mark question, they have asked calculate the specific binding energy, mass defect and specific binding energy of alpha particle. So alpha particle means what here? That is equal to what? Alpha particle means helium nucleus. This only we have done. We have solved the numerical in the previous class, right? Helium-2, that is equal to what? The alpha particle. So 5 mark numerical, one of the important 5 mark numerical based on the chapter nuclei is the calculation of the mass defect, binding energy and specific binding energy. So very simply all terms, all values they will give. The major mass of the nucleus they will give for the given element, then they will give the mass of the proton, mass of the neutron. Just we have to first calculate the mass defect by using this formula, simple multiplication, then we have to take the difference here. Next we have to calculate the binding energy using the relation 1 EMU is equal to 931.5 mega electron volt. Whatever the mass defect you have to get, you will get that you have to multiply by 931.5 mega electron volt, then you will get the binding energy. After that, by specific binding energy, specific binding energy is equal to what? Binding energy, total binding energy divided by its atomic mass number. So 492.26 divided by 56, what we have got here for the iron nucleus. Then we have got 8.79 mega electron volt. That is equal to what? The specific binding energy or binding energy for nucleus, right? Now with all these discussion, the next point, let us discuss here about the nuclear force, right? The next point we have to discuss here is about the nuclear force. So about the nuclear forces, you all know that as we have discussed in PU1 class about the 4 fundamental forces in nature. That is about the gravitational force, electromagnetic force, strong nuclear force and the weak nuclear force. So among all these 4 fundamental forces, you know that the gravitational force is the weakest force in nature, and the strong nuclear force, which is the strongest force in nature, that you are studying. So regarding the nuclear forces, we have to discuss here. This nuclear force is responsible for what? To hold the nucleons inside the nucleus, because you all know that the nucleus consists of what? The protons and neutrons. Protons having the charge is positive, neutrons, these are electrically neutral. So the net charge of the nucleus is positive, right? But the like charges are repel each other, unlike charges are attract each other, right? But here the protons, all the protons are tightly bonded inside the nucleus. Because of this, here we know that the like charges repel, but here the how these positive protons are hold together inside the nucleus, and this there must be a repulsive force, otherwise you know that like charges repel, right? That means what? The proton should repel, but the nucleus is stable. So that means what? There must be some force to hold the nucleons, that is the protons inside the nucleus, to hold the nucleus, because the nucleus is stable one. If this is the repulsive one, the nucleus will not be stable. To hold the nucleons inside the nucleus and to make it the nucleus stable, there must be some force exist inside the nucleus. That force is called as what? The nuclear force. Then what is the nuclear force here? It is the strongest force which binds the nucleons together is called as nuclear force. The strongest force. So here the one more question: what is nuclear force? Write the characteristics of nuclear force. 3 mark question, or in 1 mark. What is the nuclear force? Or write any 2 or 3 characteristics of nuclear forces. Nuclear force means what? It is the strong attractive force. The strong attractive force. The strong attractive force which binds the nucleons together. Which binds the nucleons together inside the nucleus. That is called as what? The nuclear force. The important is what? The strong attractive force which binds the nucleons, because you know that inside the nucleus only protons having the charge plus are present, neutrons are electrically neutral. If the like charges repel, according to what we know here, positive repel, negative repel, positive attract. If this happens inside the nucleus, that nucleus will not be stable if the repulsion happens. And to balance this repulsive force, the gravitational force is also not too strong inside the nucleus. So gravitational force is also weak. So because of that, some other force is present inside the nucleus to bind the nucleons strongly inside the nucleus. That is called as what? The nuclear force. The strong attractive force which binds the nucleons inside the nucleus together. That is called as what? The nuclear force. Right? So this force is responsible. Nuclear force is responsible to hold all the nucleons, or to bind all the nucleons inside the nucleus, and to make it the nucleus is stable. Right? So this binding force is called as what? The nuclear force. Now let us see some important characteristics of this nuclear forces. What are the important characteristics? So in the examination, you will get 3 mark question. Write any 3 characteristics of nuclear forces. The characteristics of nuclear forces. Let us list out here the characteristics of nuclear forces. First one, the strongest force. The nuclear force is the strongest force. Right? As you know that. It is the strongest force in nature. The strongest force in nature, right? Nuclear force is the strongest force in nature. And the next point here it is the charge independent force. The charge independent force. So it doesn't depend on the charge of the particles here, that is the nucleus. The charge independent force, right? For example, if FPP represent the nuclear force between the proton and the proton, if FNN represent the nuclear force between the neutron and neutron, and FNP is represent the nuclear force between the proton and neutron. So all the forces are equal here. The charge independent means FPP is equal to Fnn and it is equal to Fnp. That is what we are going to write here. It is the charge independent force. The nuclear force is the charge independent force. Next one, it is the very short range force. The nuclear force is the short range force. The nuclear force is, it is the short range force. Nuclear forces are what? The short range forces. That means this nuclear force is effective within a distance of only of about 1 Fermi. That is equal to what? About 10 to the power minus 15 meter. So the nuclear force short range force anta edike karteve ನಾವು. This nuclear force effective ಎಲ್ಲಿ ತನಕ ಇರ್ತದೆ? That separation between the nucleons is of the order of 10 to the power minus 15 meter. After this, the nucleons are separated greater than this distance. The nuclear force goes on decreases rapidly, right? So that means 1 Fermi. The nuclear force is effective. It is a short range. And it is effective only within a distance of 10 to the power minus 15 meter. Next, the important characteristic of the nuclear force is it is non-central forces. Nuclear forces are what? The non-central forces. That means what? They do not act along the line joining the two charges or particles, the nucleus. So these are what? The non-central forces. Nuclear forces are what? The non-central forces. The nuclear forces are exchange forces. Nuclear forces are what? The exchange forces. That is, force between the nucleons are exchangeable. That means what? PP can be exchanged, NN can be exchanged, or NP can be exchanged. So what is meant by the exchange forces? And the next property, next characteristics of the nuclear force is nuclear forces have the saturation property. They have nuclear forces have the saturation property. What is meant by the saturation property? So these nucleons, that is the nuclear force between the nucleons, they interact with only the nucleons which are present nearby to it. That is called as what? The saturation property. What is meant by saturation property? The nucleons interact with only the nucleons they are present near to it, right? So that means what? These nuclear forces, that is the interaction between the nucleons which is present, only those nucleons which are present near to it. That is called as what? The saturation property. Saturation property ಅಂತಂದ್ರೆ ಏನ್ರಿ? ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಏನು ಮಾಡ್ತಾವೆ ಅದು ಸರೌಂಡಿಂಗ್ ನಿಯರ್ ನ್ಯೂಕ್ಲಿಯಾನ್ಸ್ ಏನಿರ್ತಾವೆ ಅದ್ರ ಜೊತೆ ಅಷ್ಟೇ ಇಂಟ್ರಾಕ್ಟ್ ಮಾಡ್ತವೆ. That is called as what? The saturation property. And the next characteristic of the nuclear force is these are spin dependent forces. These are spin dependent forces. The nuclear forces are spin dependent forces. Whether the two nucleons have parallel spin or whether it is anti-parallel spin, So that is it depends. The nuclear forces depends on what? The spin of the nucleons between the two nucleons. That force exists, whether it is a parallel spin or whether it is the anti-parallel spin between the two nucleons. And also, so next important characteristic of the nuclear forces, these are non-gravitational forces. These are what? Non-gravitational forces, and also non-electrical forces, because they are charge independent, non-electrical forces, and also the non-central forces, and it is always the strongest attractive force. Strongest attractive force. So all these are the important characteristics of what? The nuclear forces. So in the examination we will get 3 mark question. Write any 3 characteristics of nuclear forces. Right? So you have to write any 3 properties. They are the strongest force in nature, strongest attractive force in nature, and these are charge independent forces. That means what? The nuclear force between the PP force, NN force or NP force, all are equal here. And non-central exchange forces, they have the property of saturation. Spin dependent forces, they are non-gravitational and non-electrical because they are charge independent, and which is the strongest attractive force in nature. So these are the important characteristics of nuclear forces. This nuclear force is responsible for what? Nuclear force is responsible for what? To hold the nucleons tightly inside the nucleus, right? So I think all these characteristics are understood, right? With all these characteristics, we will discuss the next point related to the chapter nuclei in the next class. Okay, thank you, students. So before winding the class, you have noted down this two homeworks. First one, calculate the specific binding energy of the bismuth nucleus. Its atomic number is 83 and its atomic mass number is 209. And you know the values of the mass of the proton and the mass of the neutron in terms of AMU. And the second homework is what? Calculate the amount of energy released here. Amount of the energy released you have to calculate here in this equation. It is an example of the mass is converted into energy. We have the uranium nucleus here. As we are going to discuss the nuclear fission in the next classes. So it is an example of nuclear fission. When uranium-92-235 is bombarded with the one neutron, this heavy nucleus uranium splits into barium and krypton, with the 3 neutrons are released here, and also some energy is released. So first you have to what you have to do here, calculate the mass of LHS. Alright. Next you calculate the mass of RHS. That is the equation of this equation. These are the reactants again or the product you can consider here. If you consider, then LHS and RHS. Calculate the mass defect. Delta M is equal to LHS minus RHS. So the sum of masses of the uranium and one neutron here, and the sum of masses of barium, krypton and 3 neutron. If you take the difference of these two masses, you will get some positive term. That mass defect you will get. If you multiply that mass defect into 931.5 mega electron volt, you will get the amount of energy released here, right? So calculate the amount of released in this equation. It is an example of what? The nuclear fission. The nuclear fission means what? The heavy nucleus splits into a lighter nuclei with comparable masses, with the release with large amount of energy is released. You calculate the energy released in this equation, right? Okay.